Okay, good morning everybody. So, what we have discussed, we will briefly recapitulate. So, the previous class what we have discussed some an alternate strain measure. So, D, that is the rate of deformation measure, rate of deformation measure, right, which unlike the green Lagrange strain tensor, Euler-Hermann tensor, and then Henke strain tensor. This is purely based on the so purely in in deformed configuration, right, deformed configuration or in spatial coordinate, right, in spatial frames. So, it is in Eulerian frame, right. So, and then rate of deformation tensor, if you see that the way we can express this is half L transpose plus L, where L is the deformation gradient, L was the velocity gradient, rather velocity gradient, right. So, the rate of deformation tensor is basically it's a symmetric part of the velocity gradient tensor, and velocity gradient tensor, if you can see, any square matrix can be written as a symmetric part and an antisymmetric or skew symmetric part, right. So, that was we were defining as Dij, D this first part is the rate of deformation tensor, and then that was the spin tensor, right. And then what we have seen that we also defined the rate of deformation tensor, D is related to Cauchy-Green stress tensor, a Cauchy-Green strain tensor, and the relationship, if you can recall, that E tilde dot is F transpose D F. So, rate of Cauchy-Green strain tensor, rate of Cauchy-Green strain tensor, rate of Green Lagrange strain tensor is nothing but can be obtained as a product. So, pre multiply by deformation gradient transpose and rate of deformation tensor, and then deformation gradient itself. Okay. So, this is what we can see, this is in the deformed, right, this is in spatial coordinate, spatial system, right, spatial or Eulerian spatial coordinate system, right, or Eulerian spatial or Eulerian system, where this one is the Lagrangian Lagrange or material or reference coordinate system, right, reference system, right. So, that means what if we know D, then we can come back. So, with this relationship from D we can go to E dot. So, from spatial to reference, that is what it is called, pull back operation, right. And by inverting this relationship, we can see we can go from E dot to D bar, that is called push forward operation by inverting this relationship. So, E dot to D, this will be push forward, that push forward operation, right. So, these are important relationship that is always used in not in a finite element, right. So, this is the way it is. And then we have also defined that we have also seen that either that although these are equivalent, but then integral on E. So, we can, because this is rate form, in rate form, so we can integrate into to get the total deformation, right. Integral of delta is path independent, right, path independent, whereas whereas integral on of d bar is path dependent. There is a small difference. So, although there are these two co-equivalent relationship, but this we can solve using simple example and we can demonstrate. But okay, so that was the previous class. So, now what we are going to do, we are so we have defined a number of stress measure and a number of strain measure, right. So, stress measure, stress measure, and we also define a number of strain measures, right, and so stress measure was, if you see, the first one was sigma, and then this is first Piola-Kirchhoff stress tensor and second Piola-Kirchhoff stress tensor. And we also define the strain measure, Green-Lagrange strain measure, right, and Eulerian-Almansi, Green-Lagrange, and then Eulerian-Almansi, and then logarithmic strain measure, and also the rate of deformation tensor, right. This is in, of course, rate form. So, when I am writing, this is in rate form, mind that, okay, and this is in rate form. So, given that fact, because this is a rate form or it is a strain, velocity strain, right, mind that, velocity strain. So, it will involve the time derivative, right. Okay. I mean, all these things we will not do, we will just consider only this one itself, this most widely used, okay. So, using only these two measures, the continuum mechanics can be taught. These are just alternate measures, okay. So, and then heart of this is the deformation gradient f, and also if you can see rotation tensor, and you can also see that either Cauchy-Green stress tensor, left Cauchy-Green stretch tensor, or right Cauchy-Green stretch tensor. So, these are all some kinematic measures, strain measure, or you can see kinematic measure, measure, deformation measure. So, while there will be stress and strain will relate later in the constitutive material modeling, but then as of now we can see that interrelation between we can establish interrelation between among the stress measure, among the stress measures. How it is possible? We can interrelate now, because if you see, the stress measure is depending on the deformed and undeformed configuration, depending on the reference configuration and the spatial configuration, okay. So, we can interrelate now, because we have the mapping. Without discussion on kinematics of deformation, we cannot relate them, okay. So, if you can recall what we can recall that df bar, the df bar, all these three different statement. Df bar was what? Df bar was if we want to see in terms of Cauchy, okay. So, it was n bar, and I am putting the area dA, I think about tilde, right. So, that was the this is the force, maybe force on some small area, right. So, if you can recall this one, all these measures were nothing but so there is a body, right. In that body, you are cutting, there is some so on some surface, I am assuming there is some surface, and this surface I am denoting as dA, and the unit normal is that with n bar in the deformed configuration. In the undeformed configuration, this is on deformed configuration or Eulerian, okay, and in the undeformed, the same thing, if we are denoting as d capital A and then capital N bar, okay, on this is on, okay, mind that. So, df bar is nothing but what? The area multiplied the respective stress measure. So, area is what? N bar dA. Area is represented by a scalar, that is the magnitude, and the unit normal to the area, that is n bar. And when I am writing small letter, that means it refers to deformed configuration. This is with respect to the deformed, right, deformed configuration, deformed, or the spatial or deformed configuration, or deformed configuration, all quantity in the deformed configuration we are denoting as small letter, and sigma is the stress tensor, Cauchy stress tensor. If you can recall the same relationship, see df bar we do not care, because df bar is externally, we can consider that df bar is, it is can be deformed or can be undeformed, because it is externally applied load somehow. Okay. So, if you multiply that, see some so the traction multiplied by the area will give you the external force, right, and that force measure should be irrespective of deformed or undeformed, right. So, df bar, if you can recall now, for the, this is in the undeformed, if you can recall, so this one will be P, right, you see that. So, that was the relationship now, and we also know that P bar nothing but P log first F bar into tilde, that is first P log. So, this is with respect to the Cauchy stress tensor, this is with respect to first Piola-Kirchhoff stress tensor, and this is the relationship between first Piola-Kirchhoff and second Piola-Kirchhoff stress tensor. So, we will relate. Now, how can we relate interrelate the stress measure? See, mind that in order to relate stress measure, see df bar right hand sides are equal. So, we can equate these two, that is fine, but then the most important thing is that we have to relate this n bar dA with n bar df. So, that we have to relate, if we want to relate, we have to relate the area mapping, the mapping in area, mapping among the area in area and the respective normal, right, respective normal. Area means normal, respective unit vector, normal vector on the plane, vector normal to the plane, normal to the area. So, basically we have to, what we have to do, we have to relate these. Now, if you can recall, we have related that, right. So, how the area related, how the area is related, or area along with area, that is the unit normals are also there. So, if you can recall that n bar if you can recall, n bar dA was nothing but n bar n bar J inverse D capital A. Can you see this relationship? Can you recall? J is nothing but, where J is nothing but determinant of deformation gradient, right, determinant of deformation gradient. Can you recall this? This relationship is area mapping. This is also called Nansen's relation, Nansen's relation. So, it is relating the two, area, or you can call that norma, unit normal in the deformed and undeformed configuration. Okay. So, now you combine this with this. Okay. So, if you combine this, because this right hand side, these two are same. So, what we can write? So, now we can write that n bar dA sigma tilde is nothing but capital N bar dA inner, right, and then what is n bar dA? N bar dA is okay. So, now we can write right hand side, I will substituting Nansen and then substitute the Nansen relations, right, the Nansen's relation, that in fact we have derived this. If you recall, when we were talking about kinematics of deformation, we see that how area is being, we have discussed the mapping of line segment, we have discussed the mapping of area between deformed and undeformed configuration, we have also discussed the mapping on the angle change, we have also the change in angle, the mapping in angle between two line segments, we have also discussed the mapping of the volume, right. So, here n bar dA is nothing but n bar J F tilde F inverse D A is equal to n bar dA P tilde, right. So, from there I will just cut out T and A, I will cut this, and then P will be nothing but sigma will be there. Okay. So, it is nothing but J F inverse sigma. So, this is the relationship. Okay. Or if you want to simplify it, you may want to write that F P is equal to J sigma. Okay. Okay. So, that is the established relation. So, you see the product of the first Piola-Kirchhoff stress tensor with the deformation gradient will give you the second, will give you the Cauchy stress tensor multiplied by the scale factor, that is the deformation gradient, that is the scale factor is a scalar j, j is nothing but determinant of the deformation gradient. So, this is a very important relationship, please recall that. Okay. You understand how do you relate this first Euler, and once we relate first Euler-Kirchhoff stress tensor with the Cauchy, then we also essentially related the first Euler-Kirchhoff, the second Euler-Kirchhoff, because first Euler-Kirchhoff stress tensor is related to the what? Related to second Euler-Kirchhoff stress tensor. So, please recall this relationship. This is very extremely important. Okay. It is very important to Fp is equal to J sigma, Fp is equal to J sigma. F is the deformation gradient, P is the first Euler-Kirchhoff stress tensor, and sigma is the Cauchy stress tensor, and J is a scale factor, scalar, that is nothing but the determinant of the deformation gradient tensor. So, that is the way we relate the Cauchy stress tensor with the first Euler-Kirchhoff stress tensor. Now, if you want to relate with second Euler-Kirchhoff, what do we know? We also know. So, now with second second Euler-Kirchhoff, you can do it, it's very simple, right. So, we see that F bar P is J sigma, and then what is F bar, and P is nothing but P is S F transpose is equal to J sigma, because P is what? P is nothing but F transpose, and we know that second Euler-Kirchhoff stress tensor comes from the first Euler-Kirchhoff stress tensor. We substitute the relationship, and then so if you want to write, J sigma is nothing but F, S F transpose also, right. So, an important thing also can be recalled once again. We will see the one important thing. Sigma is first, say the Cauchy stress tensor is symmetric, and S bar is also symmetric, if you see that here, because when you do F tilde F transpose, that means ultimately this product must be symmetric, because this is symmetric. So, S has to be symmetric. Okay, you see. So, S, this also represent this is, you see, also another implication, this S bar is symmetric, right, symmetric. So, that is what, if you can recall that why first Euler-Kirchhoff second stress tensor were abandoned and second Euler-Kirchhoff stress tensor was accepted, because second Euler-Kirchhoff stress tensor regain back the symmetry of the stress tensor. So, second Euler-Kirchhoff stress tensor is symmetric, that is what. Okay. So, can you see the, so see the relationship, interrelationship between the different stress measure, but in order to do that we cannot, without discussing the kinematics of deformation, the mapping between the area, we cannot relate these alternate measures of the stress. So, now when we are able to establish the relationship between these different stress measure, because we have the information on the kinematics of deformation, right, how the area is being mapped. So, that is very important. Okay. Once again you see that here F p is equal to J sigma. So, J, we have imposed a really strict condition, G is always greater than 0. So, and that is because of the regularity of the displacement field. The displacement field is one-to-one mapping, and then that will only permit, that is a piecewise continuous displacement field, as only permit a sets of measure 0. Okay, and that is what this is. Okay, it can, if it is negative, then this mapping also become meaningless. Okay. Okay. So, now what we are going to do is I will do something which is called stress power. So, a body, when a body is subjected to some force, external force, that will develop the internal forces that can be expressed in terms of stress tensor, and there will be some deformation. So, the body is will do some work, some internal work. So, external, whatever external work done is there, that is stored in the body, using some in the form of an energy, right, and that energy basically we will calculate. Okay, stress power. Why we are doing that thing? Because because this will give a important relationship, energy conjugation. Okay, stress power. Okay, so the work done. So, work done or rate of work done, or at the rate of work done, work done by internal forces, internal forces. Okay. So, it is rate of interchange of energy. This is in some way it is can be described as rate of change change in the internal energy, okay. So, that is the stress power. So, if you can recall, so here I am having a body and I am just taking a segment here. So, this segment if you see this segment, what are the external forces? Now, in this case I am assuming this is static, I am not considering the kinetic energy. Okay. I am only considering static condition just to simplify. Okay. But it is not difficult to extend it for dynamic. Okay. Considering static condition just to keep the equation simpler. I mean it's possible. So, static condition means there will be no inertia. So, what are the forces acts basically? It is T bar, right, and there will be body force, right, and if you can recall that what we have written that minus rho u u basically bar double dot. So, if we considering static case and assume and no body force. Okay. So, static case means here u bar double dot is 0 and body force means b bar is equal to 0. Okay. So, these two are 0 if they consider static condition and then no body force. So, only force is T bar. So, only internal force is just traction is the traction vector, right, traction along the surface, right, along the surface. So, we will now assess that. So, what is internal work done or rate of internal work done? So, rate of internal work done by internal forces, right, work done by internal force by internal forces, or that is nothing but power, and because it is made by stress power by stress or stress by power. Okay. Or we can write it stress power rather, that is stress power. Okay. So, how will you define that power? Power will be what? To integrate, and so where basically T, right, T it is a scalar quantity V, right, and D what is power? Power is, if you can recall from our school level physics, power was what? Force into velocity, right? Force into velocity, that was power, right? So, that is the way I am doing T, and then its power is a scalar measure. So, you have to take dot product, that is why I will take dot product, right. Now, this one what you can do, T is what? T is nothing but sigma, I mean two way we can do it. T is nothing but sigma transposes or n bar sigma, right, T, and then V, V T sigma. If you want to write it in initial form, we can write it like this: sigma I sigma Nj, sigma Ij, right. And this is Vi, this sigma, right, initial form. So, now this is, oh, I am sorry. So, this is, see, sorry. So, this is over the, sorry, this integral is over the what? Over the this, over the boundary of the small domain, and boundary is defined by what? Boundary is defined by lambda, whether the volume is defined by capital omega, right, capital lambda, capital omega. So, when I am integrating this, I should integrate over the lambda. Okay. So, lambda is basically the surface. Okay. Lambda, capital lambda, please note that, because the traction is occurring over the surface. No, that is what I am just writing, d lambda, right, fine. So, now what we can convert. So, this is basically this is a surface integral. If you can see, this is a surface integral, right, this is what? This is a surface integral, right, or integral, surface integral, or we can say line integral over the line, right. So, you can convert into volume integral. How do we convert into volume integral? This. So, this is the unit normal Nj. So, I am just so what I can do, this del, and everything in terms of deformed configuration xj. So, sigma ij, vi, right, and t, can you do that? You see that the unit normal in nj, right. So, the derivative will be xj. Please see that, xj. So, I will just simplify that, or maybe I will just can write it, and this derivative is a deformed configuration because it is small letter, and that is what I am using. So, sigma ij, and then the derivative of the whole integrand, product. So, comma j, the sigma, and then when we are writing, so see that I will differentiate it, the product of these two tensor. So, del d del a, so vi plus sigma ij vi comma j d omega. Now, you see one thing that we are considering static case, right. So, can we recall? We recall one thing, we recall the equilibrium equation, equilibrium equation, right. So, what was the equilibrium equation? If you can recall, sigma ij comma j plus b I was rho ui double dot, right. Can you recall that? Now, we did not consider body force, we did not consider acceleration, right, for simplification. So, can you see that the gradient of the divergence of the stress field is 0. So, what we can see, this is nothing but 0, this can be 0. Okay. So, what we can write here is write this sigma rj, vi comma j and d omega. Now, one more thing, if you recall, this I will write down vij. Vij is what? Vij is nothing but a velocity gradient, right. Velocity gradient is, we have denoted Vij is what? Vij as Lij, right. If you can recall previously, this is the velocity gradient. So, velocity gradient we can we have seen that how do we decompose the velocity gradient into this is a square tensor, and that can be decomposed into the schematic tensor and the skew symmetric tensor. So, this we have decomposed in terms of what? In terms of a rate of deformation tensor and the spin tensor, right. So, the rate of deformation tensor is symmetric, and W was the antisymmetric or skew symmetric, right. So, now what you see that, well, what is sigma? So, there will be two terms, one is please see this thing, this you understand, and then I will go, please see and then try to understand that, okay, what I am doing, why I am dropping this term from equilibrium and the rest of the things, right, and then velocity gradient we are deforming it, decomposing it into two parts. Now, what I am going back to here, okay, but please note that. So, I will rewrite this relations here, okay. So, what I am going to do, so stress power is nothing but volume integral, and then if you can write sigma ij dij plus wij and d omega. Now, you see that velocity gradient is decomposed into the rate of deformation tensor and the spin tensor, and what is spin tensor? So, skew symmetrics, okay. So, this is sigma ij dij d capital omega plus sigma ij wij d omega. Now, you see that dij is symmetric, sigma ij is symmetric is a product of that, and this product must be a scalar product, and this product must be a scalar product. Now, but the sigma ij is symmetric and spin tensor is skew symmetric. So, symmetric, and so when you take the product of a symmetric and a skew symmetric, right, that product is what? That product will be what? That product will be 0, right? This is 0, right? This will vanish. Why? Because you see, I am assuming that, so sigma ij, you just see, I am proving it. Sigma ij is nothing what? Sigma ij, what is sigma ji? Is nothing but minus w ji. So, it is minus sigma I j w j I. Now, when you take the product, scalar product, and this is nothing but what? This is nothing but contraction operation. So, sigma I j w I j is nothing but sigma tilde, this is nothing but contraction, linear contraction operator. So, it tensor two tensor product to give a scalar, and then when you add the two, so sigma I j, w I j and plus sigma I j w j I is 0. So, that means what? The whole product is 0. That means here, from here you can write sigma I j w I j is basically 0. Understand that? Because of skew symmetry. So, ultimately what we are going to get is this stress power is nothing but integration d I j sigma I j d I j. So, sigma I j d I j d omega. Okay, that is nothing but stress power, or if you want to write in stress power in the form, this is basically d not d sigma Cauchy stress tensor and inner product of d dv, okay, dv whole volume. So, these are the stress power. So, what we see that these are energy conjugate, right. So, from here, so sigma tilde and d tilde are energy conjugate. What does it mean? This is a very great thing. What is energy? Energy conjugate means if you take some stress measure, there must exist some strain measure with the product of which will give you the power, the work done, and these two can be related in constitutive material modeling. You see that we cannot arbitrarily relate the two things. There is another interpretation, there are two interpretations of this, I will tell you later, but this is a very important relationship, that Cauchy stress tensor is energy conjugate to the rate of deformation tensor or rate of deformation tensor. This is very important, okay, because then they are energy conjugate, they can be real. So, we can define some potential function, and then one can be obtained as a gradient of the potential function with respect to the others, okay, because they are energy conjugate. So, any quantity which are to any stress measure, I mean if we see that force, force is nothing but or work done, or energy is what? Force multiplied by displacement. Now, here in the discussion of continuum mechanics, we have defined a number of stress measure or kinematic measure rather, and a number of stress measure or kinetic measure, force measure, internal forces measure, and a number of deformation measure, that is the kinematic measure. Now, all force measure cannot be paired with arbitrary deformation measure. A pairing is only possible if they are energy conjugate. I mean that is the same thing, right, when you make friend, because depending on your nature you can make friend, right. Okay, there must be some degree of similarity between. So, similarly here also in continuum mechanics, the kinematic measure and kinetic measure, stress measure and the deformation measure can be only paired, okay, or one can be obtained from the other if they are energy conjugate. There is another important implication of that, I will tell you later. So, now we have understood this, but then another thing we would like to tell you. So, this will extend the energy conjugacy. So, you see that, so P power rho sigma dot tilde, this is the stress power, right. I mean just for the time being, I am dropping the the integral, okay. So, they are energy conjugate, but what is sigma? Or maybe we can write it sigma tilde is fine. Okay, let it be like that. But what is sigma? If you can recall sigma, J sigma was nothing but Fp, right? Fp, if you can recall, or I mean J sigma is what? Is F and P, right? Isn't it? Huh? So, J is nothing but we can write 1 by J F P, right? And what is D? How do we relate D? D is nothing but what? Del V by del X, right? So, I will write something, and why I am doing that thing, that I will explain. Wait, del V of capital X, and then by, maybe it will be a little simple if we write in indicial notation, okay? Just sigma ij dij, okay? And then sigma ij dij is nothing but del vi del small xj, and then sigma ij, this I am going to write del vi del capital X k, capital X k del j, sigma ij del capital X del xj is basically this is nothing but f I k dot, because V with respect to undeformed configuration. So, this is also true point tensor, this is in deformed, this is undeformed, reference configuration deformed, and this is nothing but what? F j k, this is the inverse of that, right? Isn't it? Right? So, so now, and we can write sigma is nothing but 1 by j f f I k p f I k p k j here we have to be. So maybe now I will start it using this. And what is sigma? Sigma is nothing but 1 by j f p, right, and f dot f dot f inverse dot f inverse, and f p is nothing but t, p f p f p, okay. So, 1 second please, I mean just allow it to remove it, okay. See, I mean this into delta, I mean because it is inner product, it does ultimately it will give you a scalar. So, this can be written like this, okay, and d bar is dij, okay, and sigma ij, okay, because this is scalar product you can change it, okay, and this is dvi dx j sigma I j, okay. So, this can be written as dvi with respect to undeformed, okay, x k small x j sigma I j, okay. So, del vi del x j is nothing but deformation I k dot, and the second one is nothing but f j k inverse sigma I j, and if you can recall now that j into sigma is nothing but f p, isn't it. So, from here I will just simplify it. So, I will write f dot, I will write f inverse and sigma, then f dot f inverse sigma is nothing but 1 by j f p bar, okay. Okay, now it will come. So, p so 1 by j I can take out because it is scalar anyway, f bar p into p, okay, 1 by j f p, you see that. So, so what we see that sigma, this inner product is nothing but 1 by j f dot, this is also an inner product only, okay, mind that, p, okay. This is also an inner product only, because ultimately this is, so you see that, okay. Now 1 by j, this is a scalar quantity, right? This is a scalar quantity. This is a scalar quantity. So I mean you can drop that, but then so what we see that sigma and d are energy conjugate that we have commented. So from this relationship what we can comment that if but F bar and P bar are energy conjugate So first Piola-Kirchhoff stress tensor and the deformation gradient are energy conjugate. You see that? So we can have a pair between this and then we can have pair between this. So Cauchy stress tensor is energy conjugate with the rate of deformation tensor, and first Piola-Kirchhoff stress tensor is an energy conjugate to what? I mean I am not considering the rate of the rate of deformation because it is time derivative, right. So first Piola-Kirchhoff stress tensor is energy conjugate to deformation gradient. These are very important, okay. They are energy conjugate, and you see the derivation here. I will explain it maybe once again. Energy conjugacy. So you see sigma, inner product d, or I mean if we change it, that does not really change. So d sigma, so d ij sigma ij, d ij vi dxj sigma. Now this is with respect to deformed configuration or spatial configuration or Eulerian configuration, right. So dj, if we want to relate it with respect to undeformed, that means we have to do little chain rule. So with respect to undeformed xj, we are relating capital Xj because capital Xj in the undeformed, capital Xj we using chain rule. So now this one is nothing but deformation gradient, rate of deformation gradient ik dot, and this one is nothing but inverse of the deformation gradient and sigma. Now f dot and sigma, and what we have learned that j, we know the relationship between first Piola-Kirchhoff and the stress tensor and the Cauchy stress tensor. So f dot 1 by j like this, and then when you take, so f tilde transpose inverse f is nothing but identity tensor. So this will drop, so 1 by j f dot p. So you see that p first Piola-Kirchhoff stress tensor and deformation gradient is energy conjugate. If you now, if I would ask you to recall one thing, if you can recall, the first Piola-Kirchhoff stress tensor is a 2-point tensor. So one of its leg is in deformed configuration, whether other leg is in undeformed. So it is referring into both. So it is a 2-point tensor, right? Can you recall that? And also deformation gradient was also a 2-point tensor. One of the leg is in deformed configuration, whether another leg was undeformed or reference configuration. You see, but both are energy conjugate. So nothing is coming out of gimmick. There is everything as a some physically meaningful sense. You see, this is physically meaningful because both are 2-point tensor, and in both first Piola-Kirchhoff as well as deformation gradient, one leg is in deformed configuration, another leg is undeformed configuration. So they are energy conjugate. Whether Cauchy stress tensor is an conjugate to rate of deformation tensor, and if you can recall, the Cauchy stress tensor is entirely defined in the deformed configuration or in the spatial configuration or Eulerian configuration, okay. And then the rate of deformation tensor is always referred to the deformed or spatial configuration or Eulerian configuration. So these relationships are extremely important. Similarly, we can also show, we will see, we can also show, I mean we will see maybe next class we can also show that green is an second Piola-Kirchhoff R energy conjugate. So basically the power will be given, stress power will also be given by basically E tilde dot and inner product between the second Piola-Kirchhoff stress tensor and the rate of Cauchy-Green deformation tensor. These are, so these three pair you should recall. This last proof I will do that, okay. E and AS are conjugate, will be conjugate, okay. So there is 3 pair of conjugacy. These are extremely important, okay, especially in constitutive relationship, okay. So how do we get? So that's what basically our main intention was to prove the energy conjugacy, and that's what we didn't consider the body force, or we didn't consider the inertia force, or we didn't consider the I mean those things, okay, because in order to prove the energy conjugacy we can drop those terms, okay, just to make the terms little less. You understand that? So energy conjugacy you must understand, must be able to appreciate that what is energy conjugacy. So now when we define the stress tensor, we shouldn't say the way we were defining when we were a baby, second year, that stress is measure stress tensor. What is stress? Stress is the force per unit area. No more. Stress is not force per unit area. Of course, the area is associated, but today we are going to define stress, that is a kinetic measure, so as a force measure somehow, that is energy conjugate to some deformation measure. Okay. So, the energy conjugacy is hard in defining the kinetic and kinematic measures as far as discussions in this continuum mechanics, deformable body mechanics is concerned. Okay. One more thing here is what I am going to define is compatibility of strain measure, okay, of strain measures. So, if you can recall that in a body, we can have only 3 component of deformation, right, 3 component of deformation, right. So, U is a 3 matrix, right. So, it is U tensor, it says 3 component U1, U2, U3, right. But how many strain measure we are having? But the strain measure, the strain measure, how many strain measure we are having? Strain measures are, okay. If we do, if we consider of course the symmetry, then there will be, ideally it is 9, right. So, any strain measure, any strain measure is basically what, 3 by 3, 9, but if you consider symmetry, if you consider symmetry, then it can be sim, okay. So, 3 by 3 basically, you are having the so 9 strain measure, maybe 9 strain component. Now, if we see, component, you are defining something. So, you have a strain displacement relationship in 9 relationship, right, 9 component, right. If you can recall, so or if you can recall, Eij is what? Eij, if you can recall, Eij was what? Eij was what? Del Ey del Xj plus half half what? Del Uk del X one second. That was the relationship, right, or in indicial notation if you want to write, it was up, the nonlinear. So, how many equations were there? You can recall 6 equations, right? 6 equations were there, right? 6 equations. How many displacement component, right? So, if you consider symmetry, you will have 6 component, right? 6 component, symmetry, 6 component. So, you see that we have 6 number of strain displacement relationship, whether we have 3 independent component, right. So, we have 6 equation, right, 6 equation relating strain with this. However, there can be only 3 independent components. There can be only 3 component, right? 3 component independent here, 3 independent displacement component, right? For UR, right? So, see, so then this is a what determined system, you can see, right? So, this is a what determined system, right? This is an overdetermined system. And how many degree of overdeterminacy is 6 minus 3 is equal to 3, right? There are 3 degree of overdeterminacy, right? Isn't it? So that's what, so the strain measure thus, the strain measures must be interrelated for uniqueness of the displacement field, for uniqueness of the displacement field or deformation field, okay, displacement or deformation field. And this and then the equation, so this results in the equation of compatibility, the compatibility equation, okay, compatibility equations. So what is the equation of compatibility? Equation of compatibility is nothing but the 6 strain measure cannot be independent because they can only be they are only related to 3 independent components. I mean, you can always find out the displacement field by integrating the strain field, because strain displacement relationship is a differential relationship, right. So you can always integrate the strain displacement relationship to get the stress field, to get the displacement field, but you cannot get that because you have 6 equations whether you have 3 independent components. So the strain measure must be interrelated, and the interrelationship between the strain measure is expressed by compatibility equation, which is an important equation. So compatibility equation, in indicial notation I am writing most generalized I j k, Levy symmetry symbol, L m n, and strain measure epsilon j m comma k n is equal to 0, okay. So this is the equation of compatibility, okay, and these are the Levi-Civita symbol. So these are the Levi-Civita, these are the alternating symbol, and whether this is the strain, okay, this is maybe strain, this is the strain measure, strain, okay, you see there. So for simply for 2 dimension I can give you an example. I will discuss these things when I will come to elasticity in 2 dimension. So there is a 2 different, so you please see that, okay. But be aware about the compatibility. So what is compatibility? That means that enforce the uniqueness of the displacement field, okay. So this is, and this compatibility is essentially mostly applicable for inelasticity, okay. You use in elasticity, this one, in elasticity, we use this thing in elasticity, okay. For large deformation generally we do not require to use the compatibility, okay, we use it for only elasticity. So you understand what is compatibility, right? Okay, so for this today, this is it. So next class I will summarize this, and then we will start our 3rd chapter, okay. Okay, thank you very much.